So we talked some about isotopes. As a reminder, an isotope is an atom of one specific element that has a set number of neutrons in it. One atom, so let's say I have an atom of carbon. Carbon will always have 6 protons, and if it's a neutral species, 6 electrons. But one carbon atom can have a varying number of neutrons. We have carbon 12, carbon 13, and then radioactively we have carbon 14 being produced in the upper atmosphere. Carbon 12 and 13 are the natural abundance carbon atoms that are in our world, though. So what I mean by that is that if I have 2 atoms of carbon 12, one may have 6 neutrons, one may have 7. We are going to do the math in a little bit to figure out like the actual percentages of each one, but they are what make up the natural abundance of our world. So we've talked about isotopes, again, identifying number of protons, neutrons, electrons. Isotope just means a different number of neutrons in the nucleus within the same atom, or same type of atom, not the same exact atom, the same type of atom. But how do we know that? And how can we calculate what should actually come out of this? In this module, we should be able to interpret and sketch mass spectra data. Mass spec, or mass spectrophotometry, is a way for us to identify what isotopes are present for a specific species. And you should also be able to determine atomic mass, which we also call your atomic weight, or molar mass, molecular weight, formula weight, all those terms, from an element, for any element, from the isotopic abundances and masses. So first, this is just what a mass spec looks like, generally speaking. There are different types out there. They can get really, really big, they can get really, really small. But a mass spectrophotometer, or mass spectrometer, looks at, again, it's just going to separate my particles out to figure out what size they are. And then from there, I can figure out how many neutrons are in its nucleus. Generally speaking, what's happening here is the sample is injected into the mass spec, and at that point it is vaporized, meaning we force it into the gas phase. A vapor is something that is in the gas phase when otherwise it wouldn't be if we hadn't forced it under those conditions. So we force the sample into the vapor phase or into its gas phase. We then charge that species. So here, we vaporize it, now we ionize it, meaning we give it a charge. Most often, the mass spec is going to give your particle a positive charge to it. Most often, a positive 1 charge. Not always, there are different types of mass specs. Most commonly, you're going to have a charge to it with a +1 charge. We then send it through a series of magnetic and electric fields. The electric field is accelerating the particles, making it move faster and faster. The magnetic field is actually used to separate the particles, and it's separating them based on what we call your mass to charge ratio. Since each particle has been charged the same way, each particle is given the same charge, this really is separating them out by mass. It's just that, if I'm sending something in a magnetic field, a neutral species is not going to be affected by that. We have to use a charged particle to actually affect the particle's velocity and movement throughout the system. So basically, we're really separating by mass here. Once it separates through the magnets by mass, it hits your detector, and your lightest particles hit separately from your heaviest particles with everything else falling in between. So the mass to charge ratio, or again, in turn the mass, because they all have the same charge, will separate out those particles based on the mass of that particle. And that's how we can detect what actual particles we have. Mass spec is used to identify things all the time. We use it to identify unknowns. We can make a new compound. We can break up the compound, identify what it is, protein analysis, all kinds of stuff is done with mass spec. Drug analysis, etc. But on a most simplistic form, we can also use it to identify isotopes of an element. When we run a mass spec, we get a data that looks like, the resulting is data that looks like this, what we call a mass spectrum. Mass spectrum is just the spectra or the analysis, the graphical analysis of the data that was observed in the mass spec. Here we've got one for gallium. And so it says here, an example, the mass spectrum of gallium, Ga, is shown below. The atomic mass of gallium is 69.7 AMU. Which of the following statements is correct? Well, let's look at what the data is showing me here. I've got a relative abundance percent, so this is telling me how many particles I have with that mass. And then my mass in AMU. Again, this is actually my M to Z ratio, my mass to charge ratio, but again, because they're all charged to +1 charge, it's correlating to the mass of that species. I see a peak of 71.9 AMU, I have 39.9% abundance. At a peak of 68.9 AMU, I have a 60.1% abundance. What this means is about 60% of the particles analyzed had a mass of 68.9 AMU. About 40% of the particles analyzed had a mass of 71.9 AMU, as observed in the mass spec. So let's look at the options here for questions. Number 1, all gallium atoms weigh 69.7 AMU. Absolutely not correct. In fact, we don't have anything here at 69.7. There's no particles that weigh this. Or no gallium atoms weigh this. My atomic mass of gallium is 69.7, yes, but none of them actually weigh this. The atomic mass of gallium is the average of 68.9 and 71.9. Also not correct. If I was to average 68.9 and 71.9, I would find my molar mass to be 69.9 AMU, and it is not. It is actually 69.7 AMU. So by default, I can tell it's number 3. Now, I'm going to talk about the weighted average of isotopic masses when we actually do calculations in just a minute. But that's what I want you to realize is that gallium has 2 naturally occurring isotopes. Gallium-69, gallium-72 is what we call them, because this is closest to 69, this is closest to 72. But neither one is the 2 particles together. It's about a relative weighted average of their masses that make up the actual atomic mass of the particle itself. So the atomic mass of gallium will be closer to 69 than 71 because there are more atoms that weigh 68.9 AMU. That is absolutely correct. We see that the true mass, 69.7, is closer to 68.9, and that's just because, it's a weighted average. I'm looking at all the particles coming through, 60% of them weighed 68.9. Therefore, if I'm going to take a sampling of gallium atoms, I'm going to say its molar mass is going to be closer to that than the 71.9. Let's look at a couple other examples. Now, these are from your book, and there is a note here. Be cautious when working through textbook problems because it can be difficult to read the graphs with the precision they seem to expect based on the answers. If you're unsure, just come see me and we can talk through it. But what about these? Estimate the atomic mass of each species below. Here I've got silver 107, silver 109, and separately we'll talk about chlorine 35 and chlorine 37 in just a sec. So silver 107 and silver 109. What I see here is not quite the same as the previous page. Here I've got 150. The previous one only went up to, 60%, roughly. This is normalizing it up to 100. And I'll stop flipping the screens on you, I'm sorry. This is going up to 100. My top peak here at 100, my second peak not far behind. So the 2 ways you're going to see mass spec data presented is either it being normalized, so the highest intense peak is normalized up to 100, or is factored up to 100. Everything else is normalized to that peak, and that's what they've done here. They said that we have 2 peaks that come through. We have silver 107. We have silver 109. Those are my 2 isotopes. Silver 107 will have a mass of around 107 AMU. Silver 109 will have an atomic mass unit around 109 AMU. And I want to know what the mass of silver is. Now, I can look at the periodic table, yes, but let's try to delve through. Let's try to analyze this and say, instead of looking at the table right away, let's see if I can figure out what the mass might be based on the data here. It's saying that the highest peak I have is 107. Now, the peak at 109 is very close to that. Not quite there, but very close, right? We're not quite hitting 100%, but we're very, very close. What this tells me is that, again, it's going to be the average of these 2 peaks that make up what we call your actual atomic weight of silver. So I look at these 2 and I say, okay, it's going to be between 107 and 109. And it's actually going to be pretty close between them. It's going to be a pretty close average, so the peaks are almost identical. If they were identical, I would assume it would be an average of the 2. But the peak at 107 is slightly higher than the peak at 109. So I'm going to say, I know my X value is between 107 and 109. But I know it's going to be slightly closer. It's not going to be quite an average of 108. It's going to be slightly closer to 107, except that the 109 is a pretty high intense peak as well. So it's going to be really close to 108. So I'm going to guess 107.9 AMU. It's pretty close. The 109 isotope has a lot of impact on it, but it is still slightly closer to 107. And when I look up the true value on the periodic table, I see it as 107.87 AMU. So our guess was actually really, really close. What if I look at the chlorine one? Chlorine 35 and chlorine 37. I know that my value that I'm looking for will be somewhere between 35 and 37. But my chlorine 35 has been normalized to 100, whereas my chlorine 37 is down here. Chlorine 37 is less than 50%. Well, I definitely know it's going to be less than 36. But the chlorine 37 peak, the difference between these two peaks is pretty big. So I'm going to mentally say chlorine 37 is maybe 1/3 that of chlorine 35. And so I'm going to kind of try to think about that difference between these two. And I'm going to say, okay, between 35 and 36, we're going to be not even quite maybe halfway between the two. You know, if we think about the difference, what I'm doing here mentally is I'm thinking about the difference between 35 and 37. The difference there is a value of 2. Chlorine 37 is about 1/3 of that. Well, if I look at 1/3, if I look at 1/3 of 2, that gives me a peak of about 0.67. So I'm going to guess that the chlorine is going to be maybe 35.7 AMU. But then I look and I'm like, actually, you know, that 107, 109, I guess that at 107.9, and that's actually pretty close. The chlorine 37 is actually a lot lower than that. So maybe 0.7 isn't low enough. What if I said 35.5, 35.3? These are good guesses, and I would give you full credit for this guess, okay? Now, the actual is 35.45. Most important part is I am realizing that it's not going to be near 36. It's going to be closer to 35, but it will still be between the two. The 37 still does have an impact on the mass of the overall peak, but it is closer to 35. So again, if I gave you a spectrum like this and asked you to guess it, it would be either a multiple choice question, or I would make it somehow very obvious. Like I would give this full credit. I would give this full credit. I would even give 35.7 AMU full credit. I would not give 35.9 or 36. Full credit, because it's just not that close. So what do we do with all of this? All of this is how we get the atomic masses. This is that value on your periodic table. We have said on the periodic table that is your atomic mass unit. That is what we're talking about right now. We've also, if you've had chemistry before, you know that's also the equivalency of your molar mass or your atomic weight, which is also correct. We'll talk about that later on in this chapter. But first, let's figure out how those masses were found. They were found from the isotopes of the elements that we have, the most naturally occurring isotopes. Some definitions we need. So 2 important definitions that you have learned in school before is percent and fraction. Percent is your part divided by whole times 100%. If I went to class today and said, you know, what percent of the class of students are wearing a purple shirt? I would count up all the students wearing purple, divide it by all the students in the entire room, and times it by 100. That would give me the percent. Possible values here are from 0 to 100, and percent is your unit. My fraction is your part divided by whole. We just don't multiply by 100, right? So if I said what fraction of students, I would just take how many students were wearing purple divided by the total number of students in the class, and I just wouldn't multiply it by 100. That would give me my fraction. Possible values here, 0 to 1. We're going to take advantage of this concept on this example. So first, atomic weight. Atomic weight is a weighted average of your isotopic masses. Basically, we look at what species are the naturally occurring abundance isotopes of an element and how much abundance they have. And that's what we're going to actually use to find the atomic mass unit of that element. So how much of that element, if I go way out a specific amount of element, how many particles should that represent is really what we're getting back to. An example of a weighted average. Most students can do weighted averages okay. Most students aren't great at them though. But let's look at a weighted average. This class is taught on a weighted average. You've got, exam scores, you've got other scores in there, quiz scores, etc. This class is great on a weighted average. Let's use an example where we have a class that has a 50% midterm average, a 25% final exam average, and a 25% lab average. Let's say we got an 82 on the midterm, we got a 78 on the final, and we got a 97 on the lab. If I wanted my class average, so I wanted my grade, I would say, okay, well, that's 0.25. Sorry, let's actually start with 0.5. I was looking at the wrong thing. 0.50 times 82 plus 0.25 times 78 plus 0.25 times 97. So again, what I did here was I put these back in fractional form. 0.5 or 50% is 0.5. 25%, 0.25. There should be a decimal place right here. I apologize. I should have 50 decimal point on your slide. I missed that when I was making your slides because of sig figs. And then 0.25. I've taken them out of percent, put them back in fractional form. Now I multiply it so that 50.5 times the 82 is the percentage that midterm is contributing to my final grade. The 0.25 times 78 is the percentage that final exam is contributing to my overall grade. And the 0.25 times 97 is the percentage that the lab is contributing to my overall final grade. When I calculate this out, I'm going to get a calculated answer of 84.75. Due to sig figs, I'm going to round up to an 85. You would have an 85 in the class. The same thing is how we find your atomic mass unit of your elements. We look at the species and see what are their natural abundances, what is the percent of that natural abundance, and what is the atomic mass unit. Again, AMU, atomic mass unit. Of that specific isotope. So for example, magnesium has 3 naturally occurring isotopes: magnesium 24, magnesium 25, magnesium 26. We can see here its atomic mass unit and its percent abundance for each species. Let's go ahead and calculate the atomic weight of magnesium based on the data that were provided. The atomic weight here would be 23.9850 AMU times 0.7899. Again, I'm putting this into fractional form because that's how we're going to do it. We're going to multiply the mass times the fractional abundance. I add that to the next one, 24.9858 times, and that's AMU, 0.1000. I'm going to run out of room here, plus 25.9829 times 0.1101, and that is AMU as well. And I'm keeping all 4 sig figs throughout, okay? When I multiply these, I'm going to add these up. I'm going to do my sig figs correctly. Check your sig figs. Each multiplication will give you 4 sig figs, and then you will find at the end that you will have some species that have 3 decimal places. One of them has only 2. So you need to make sure that your final answer only has 2 sig figs. Check your sig figs, and so if you're not sure, come see me and I will help you. But calculate it out. I just don't have room to write it all out. I apologize. 24.31 AMU is the answer I'm going for here. But what does this mean? What this means, 24.31 AMU for magnesium. If I look back at the periodic table, I would see that the mass of magnesium is 24.31 if I round to 2 decimal places. It's listed as 24.3050 on the table itself. I have just confirmed that the mass of magnesium, the atomic mass unit, is 24.31 AMU. by taking the mass of each individual isotope along with its fractional abundance. These are the naturally occurring isotopes. So again, we're going to do some more calculations on this as well, and we're going to see how the table is designed. Why is magnesium 24 less than 24? Why is magnesium 25 less than 25, 26 less than 26, etc.? They're very similar. They're very close, which is why we call it that. But again, those masses are dependent upon how many protons and neutrons we have in the system. We say magnesium 24 for ease. We also said a proton is about 1 AMU. We said a neutron was about 1 AMU. That doesn't mean they're exactly 1 AMU, which is why the masses are slightly lower. So let's look at a couple more examples. Most often, I would provide you, if doing a calculation, the mass, or the mass would be what we're looking for. But there is one mass that you have to memorize. That is specifically the mass of one carbon-12 atom. What I mean by that, by carbon-12 atom, again, means that it has 6 protons, 6 neutrons, and we don't care so much because they don't add much to the mass, but 6 electrons. One carbon-12 atom is exactly 12 AMU. The definition of atomic mass unit, or AMU scale, is 1 AMU is equal to 1/12 of a carbon-12 atom. So 1 AMU equals 1/12 the carbon-12 atom AMU. It has been specifically defined that way. The entire periodic table, and you're going to see that in the very next module that you're going to cover in this outside of class in this course is module 2D, where it talks about the periodic table and the construction of the periodic table. But the entire periodic table has been set on carbon-12 atoms, or carbon. Carbon is the most abundant element there is. If you take all the compounds in the entire world, take everything in the entire world, and in one pile, you put everything that has carbon in it. In the other pile, you put everything that does not contain a carbon atom. The pile with carbon would be bigger. In addition to that, carbon has 2 naturally occurring isotopes, carbon-12 and carbon-13. And carbon-12 is, we're going to do the math in a sec, but about 99% of all carbon atoms are carbon-12, about 1% are carbon-13. Carbon-14 is in a much smaller percentage that is produced up in the upper atmosphere. It is a radioactive material. The entire table based on carbon-12, okay? So again, 1 AMU is 1/12 that of a carbon-12 atom. You have to know that that carbon-12 is exactly, meaning no limit to sig figs, 12 AMU. So 12.0, repeating, AMU is a carbon-12 atom. That's going to come back into play in just a couple examples. First, let's work a couple others. Here's 2 conceptual problems. One I can do conceptually, or one I can actually do by math. I'll do it both. There are 2 naturally occurring isotopes of europium, europium-151 and europium-153. And it tells me the mass for europium-151 is 151.0 MU. The mass of europium-153 is 153.0 AMU. What is the approximate natural abundance of europium-51? Now, I did pull this question from our online homework system. And in the system, it said the options were 0%, 100%, 50%, and then I think it was like 67% and 33%, roughly speaking. So I have 2 naturally occurring isotopes. I want to know the approximate natural abundance. It tells me here the atomic mass of europium is 151.96. That means that the actual mass of europium, if I take a sample of europium, it would, if I have one, we'll talk about mole in just a bit, but if I have 1 mole of europium atoms, it would weigh 151.96 grams, okay? If I was to figure out the weighted average like we did for magnesium, it would come up to 151.96 AMU. I know the only 2 things contributing to this are 151 europium and 153 europium. 151.96 is very close to the middle, right? That is very similar. That's approximately 152 AMU. I want to know how much 151 is contributing. Well, if it was 0, it's definitely not 0, because if it was 0, the AMU would be 153. It would only be contributed by the 153. It's not 100% either, because if it was 100% 151, then the mass of europium would be 151, not close to 152. It is 50%, because it is about in the middle. Now again, this is the approximate natural abundance. It's about 50% europium 151, about 50% europium 53. So if you had this as a multiple choice question, hopefully you would recognize it is not 33%, because it's slightly closer to 151. It's also not 67%, because although it is slightly closer to europium 151, it's about middle ground. What if I actually wanted to solve the numbers here, though? How could I go about that? Here's going to be some algebra. The way we do this, we're going to set up just like the magnesium problem. The atomic weight is equal to the fractional abundance of europium 51 times the mass of europium 51 plus fractional abundance of europium 153 times the mass of europium 153. Now the issue is I know the atomic weight. That is 151.96 AMU, but I don't know my fractional abundances. I'm going to let this be represented by X and this represent by Y. I have two unknowns and one equation. Normally you need two equations, two unknowns, but I do have a second equation. I know that there's only two naturally occurring isotopes. Therefore, if I said percent, the percent of X plus the percent of Y would have to equal 100%, but that means X plus Y has to equal 1. The fractional abundance of the two of them added together have to be equal to 1 because they're the only two things contributing. So for example, I know it's roughly 50% each. I know roughly 50% of X. I know X is roughly 50%, Y is roughly 50%. That adds up to 100%. That means 0.5 plus 0.5 is 1. I want to figure out the exact values though. I'm going to rearrange this equation here, and I'm going to say, okay, well, Y is equal to 1 minus X. I'm going to take this and substitute it in for Y in my equation. Now I've got 151.96 AMU is equal to X times 151.0 AMU plus 1 minus X times 153.0 AMU. I'm going to drop the units here in a sec because we're going to go to percentages anyway, and the units just kind of make it messy to do. Most of the time you cannot drop units. On an example like this, I would not care if you dropped the units and just worked with your numbers. Let's go ahead and work this through. 151.96 is equal to 151.0x plus, this is distribution, right? I need to distribute this through the equation. So 153.0 minus 153.0x. I'm going to put all my integers on one side and all my variables on the other. It does not matter which side goes to which. To do this, for this one, I'm going to subtract 153.0 from both sides of my equation. This is going to give me negative 1.04 is equal to 151.0x minus 153.0x. Now I can combine these two, and I'm going to have to move up here. I apologize. This question was supposed to be intended to do just conceptually, but I'd like you guys to see the examples as well, so we will do another example like this, and getting more practice is helpful. I have negative 1.04. This is equal. Now I'm going to take that 151 minus the 153. That gives me 2.0x, again 0.0, because it's precise to the tenths place. This is precise to the tenth, like TENTH, or the first decimal. Negative 2x. I'm going to solve for x by dividing both sides. That is a negative there. Dividing both sides by negative 2.0. And what I get is 0.52 is equal to x. But again, what does that mean? I've defined X previously. I said X is my fractional abundance of 152. Of europium 151. That means that the approximate natural abundance for europium 51, 52%. I'm going to take that and put it back into percent form. Why? Well, percent is just easier for most of us to see, to be honest. But it means that we were right in our assumption that it's about 50%. So you can solve this numerically as well, as long as you're giving the masses of both, and you could even look at the periodic table to find the atomic weight of the species. Let's do the next example here. Nickel has a higher atomic number than cobalt, but cobalt has a higher atomic mass. That statement itself is kind of unique. We're going to talk about this in Module 2D, but Mendeleev, who is known as the father of the periodic table, Mendeleev was the first person to actually organize the elements of the periodic table in a logical pattern. People at that point had been trying to start to organize the elements, but there was and the patterns they were finding were working, except Mendeleev was the first one to realize he had to leave spaces for elements that had not yet been discovered. And he was able to actually predict properties of elements as yet discovered based on his organization. So other people, yes, they had been figuring out to start to organize them. They had been trying to put the table together, but they hadn't thought to leave spaces for things that were yet missing. He was the first one to come up with that concept. And so when Mendeleev designed his table, it was incorrect in the sense that he thought it increased by atomic mass. It actually increases by atomic number, as we know now. But most of the time in the table, if you look at the periodic table, most of the time, the periodic table you will see is increasing by mass in addition to atomic number. Every so often you'll see it flip where things like cobalt and nickel, cobalt has a lower atomic number. It's one number lower than nickel, but it has a higher atomic mass. And this again is due to those isotopes that are making up that mass of the element. So cobalt 59 has 100% natural abundance. That means that all of the atomic mass unit of cobalt is just due to that one isotope. The 5 stable isotopes of nickel are nickel 58, nickel 60, nickel 61, nickel 62, and nickel 64. Which nickel isotope has the highest natural abundance? Well, you have to go to the periodic table, which I don't actually have in front of me. A great website, if you are practicing, is ptable.com. It's very colorful, but you can also look at different properties. You can click on elements, you can click on different types of groups, etc., and find a lot of information very quickly. It's a great website. If I look at nickel, I see that nickel is listed with an atomic mass unit of 58.693. What I know is this is equal to the fractional abundance of nickel 58 times the mass, which would be around 58, plus the fractional abundance of nickel 60, which is going to be around 60. I'm going to run out of room here. Fractional abundance of nickel 61 times the mass around 61 plus the fractional abundance of nickel 62 times the mass of nickel 62, which will be around 62 AMU, plus the fractional abundance of nickel 64, which will be around 64 AMU. I know all of this, this giant computation here has to equal out to 58.63. I want to know which isotope has highest natural abundance. Well, 60, 61, 62, and 64 are all going to pull the atomic weight of nickel above 60, right? I've got 58 and 60, and then I've got 3 isotopes above 60. Those 3 isotopes above 60 are going to have a mass unit much higher than 60, especially nickel 64. So they are pulling the mass up. The mass itself is only 58.693, or about 58.7. That means that the most isotope that has the highest natural abundance has to be nickel 58. There's no way I can get a mass unit of 58.693 unless that one is contributing a very large amount to basically counteract or counterbalance all the other species. And so this is where you're trying to put that concept into play and see, do you really understand the concept of how that atomic weight is found? What about this one? The atomic weight of carbon is 12.011. Given that naturally occurring carbon consists of only two isotopes, carbon-12 and carbon-13, and given that the mass of carbon-13 is 13.00335, I do apologize, there is a typo in this slide right here. This should be 0.00335 AMU. I did not realize that that was incorrect until I was teaching in class the other day. What is the percent abundance of each isotope? And the 335 is just making it more precise in the measurement, so we're going to use that in our calculations. We're going to do this very similarly to how I just did this, the European problem when we actually did it by math. We know that the atomic weight of carbon is equal to the fractional abundance of carbon-13 times the mass of carbon-13, or carbon-12. I apologize. I like doing things in order. My brain likes it better. Times the mass of carbon-12 plus the fractional abundance carbon-13 times the mass of carbon-13. I know it's telling me the atomic weight of carbon is 12.011, so I know this is 12.011 AMU. I'm told that carbon only consists of two isotopes, carbon-12 and carbon-13, naturally. Cool. And I'm told that the mass of carbon-13 is 13.00335 AMU. And I want to find the percent abundance of each isotope. Unlike the European problem, though, I'm not given the mass of carbon-12, but that's because that is the only mass I need to have memorized. I need to know this is exactly 12 AMU. Now, I don't know the fractional abundances. I'm going to let this be represented by X and this represented by Y. X is going to, so again, we're going to let X represent fractional abundance. Carbon-12, and we're going to let Y represent the fractional abundance carbon-13. If they are the only two isotopes, I know the percentage of carbon-12, the percent abundance of carbon-12 and the percent abundance of carbon-13 have to equal up to 100%. That means fractionally, X plus Y has to equal 1. I'm going to rearrange this and say, well, then in that case, Y is going to equal 1 minus X. And I'm going to substitute that into my equation. I'm going to say 12.011 AMU is equal to X times 12 AMU. Again, that 12 is exact. It is not limiting my sig figs there. Plus 1 minus X times 13.00335 AMU. And now I'm going to go ahead and start solving this algebraically. 12.011 AMU is equal to 12x. I'm going to drop the AMUs right now just because, again, I'm going to be solving percentages anyway, and it's going to just make this calculation easier to see because we're going to have lots of things going on here. I'm going to distribute this through the 13 times 1, the 13 times x. So plus 13.00335 minus 13.00335x. Let's see. Let's combine your variables. I actually like the x's on the other side, so I'm going to put both my x's on the other side. So I'm going to say, I'm going to subtract 12x from both sides. So I know some students need this written out a little bit differently. Sorry, GoodNotes updated their app, and I'm not used to exactly where the buttons are anymore, and it's throwing me off. Okay, so I'm going to say minus 12x minus 12x minus 13.00335x plus plus 13.00335x to get those on the same side. I need to add the 13.00335 to each side. When I do that, I would have 12.011 plus 1.00335. This is precise to here because that 12 isn't exact. X is equal to 13.00335. Let's go ahead and subtract this 12.011 from both sides. And I do apologize. I'm not used to doing my math this way, but I've realized recently students are really struggling with where to put their integers and how to show the algebra. 1.00335x. Normally I just do the math, but yeah, like I said, I know students lately have really been struggling. So I'm trying to show you guys how it's all coming together. Sig figs here, 3 decimal places, 5 decimal places. I'm going to keep this to 0.99235. The 2 is where my sig figs end, though, the 0.992. I'm going to hold the 935 just for sig figs purposes, or for rounding purposes in just a minute. Now, the line here is just trying to separate out the different pieces. Now I'm dividing by 1.00335 to isolate x. And I get an x value equal to calculated 0.989. 0.36727. It's a big number, right? Remember my sig figs are 1, 2, and 3. This has 3 sig figs. This had 1, 2, 3, 4, 5, 6 sig figs. My x itself is equal to 0.989, but that does not answer the question. The question was, what is the percent abundance of each isotope? This means X represents the fractional abundance of carbon-12, which means the percent abundance is 98.9%, which means for carbon-13, it would be 1.1%. Now I've solved it. That is the most difficult way to, difficult question I know how to ask. I don't know how to ask it more difficult than that, if that makes sense. So if you can do that, you can do anything. Does that mean that's the only type of question I'm going to give you? No. There's 3 different variations I could do. I could do it like we did the magnesium question, where I give you the percentages and the masses, and you figure out the overall answer. I could give you a couple of the say I could give you 2 of the masses and 3 percentages. You would have to figure out algebraically the third piece. What if I gave you 3 masses but only 2 percentages? You should know the percentage adds up to 100%. And then, of course, you can do it this way as well. So these are, the different ways we can do this. It's algebraic manipulation at that point. And the last question in this module, chlorine exists in nature as a mixture of 2 stable isotopes, chlorine-35 and chlorine-37. Which of the following represents the percent abundance of chlorine-37? Now, earlier in this module, we did see the actual peak, the mass spectrum, so we should be able to answer it if we thought back to that or went back to that part in the video. But we don't have to either. We can just think about what this means. If I look up chlorine on the table, the atomic weight of chlorine or given in the question as well, but I don't even need to give it to you in the question. I could just say the question without putting it in there, because you will have a periodic table on any assessment you do. And on homework, you can pull up a periodic table. Atomic weight is 35.45 AMU. I know that the 2 things contributing to this are chlorine-35 and chlorine-37. I want to know the percent abundance of chlorine-37 specifically. Well, it's definitely not 100% because the answer is not 37. It's definitely not 0% because the answer is not 35. It's not 50% because the answer would be 36. It's not 77% because the answer would be closer to 37 than 35. So the answer must be chlorine-37 has a percent abundance around 23%, which is why it's closer to 35 than even 36.